Okay, great. Welcome everyone to our meeting of the Culture Seminar in Differential Algebra. And it's my pleasure to introduce Thomas Dreyfus, who will talk about computing Galois group of order 3 equations. Please.
Okay, so thank you very much for the invitation. It's very kind from you. So I remember that I used to do a remote talk at the Culture Seminar before the COVID. So before it was a habit of everyone to make remote talk. So I'm happy to was the first to do that. So let's continue in this tradition of making remote talk. So I'm going to speak about joint work in progress with Marina Poulet, which is actually in Grenoble, about the computation of the Galois group of order 3 equation. So let us precise a little what will be the background on this talk. So I'm going to consider a field equipped with an automorphism, so a difference field. So in this talk, everything will be of characteristic 0. You can consider the general problem, or you can have in mind some concrete example. So the most reasonable example is the shift case. So K will be the field of rational function, and the automorphism is just a shift. So you map f of x to f of x plus h, where h is a complex number. So we used to want phi to be not cyclic, so h will be non-zero here. Or you can consider the Q difference case. So for instance, you can take phi of f of x maps to f of qx. So again, I don't want to have something cyclic, so I should ask that q is not a root of unity. But to be simple, just assume that q is not of modulus 1. And up to inverse it, you can assume that q is strictly bigger than 1. And for a technical reason that will appear later, we'll have, in this case, have to take the ramification. And the third case, which is maybe the most interesting, is the Malor case. So in that case, the automorphism is a Frobenius automorphism. So f of x maps to f of x to the p, with p an integer bigger than 2. And again, you have to take ramification because you want phi to be an automorphism, so you want to invert it. And this example is on interest for the following reason. So the Malor equation naturally appear in the computer science. So if you take an automatic sequences, so basically it's a sequence that may be read by an automata. So the complexity of the sequence is not so big. If you take the generating series of such a sequence, then you find something that is solution of a linear Malor equation. And it has been proved that similarly to what's happened for the E function, if you consider a Malor function that is transcendental, then most of its values are also transcendental. And it's very interesting because it's almost impossible to prove that a number is transcendental. We know almost nothing. So we reduce the problem of proving that a number is transcendental to the problem of proving that a function does not satisfy algebraic equation. And as we will see, this problem may be solved by a Galois theory of difference equation. So it's a motivation to study this problem. And the last case is the case of elliptic function. So you have two ways to represent an elliptic function. So you may represent it with Weierstrass function, so a meromorphic function on C with two different periodicity. And in that case, the automorphism will be f of x mapped to f of x plus h. And again, you want phi to be not periodic, so it means that h is not a torsion point of the curve. So difference equation on the form E you can find in various contexts, and for instance, in when you want to study the nature of generating series of works in the quarter plane or 3/4 plane, you find, depending on the situation, equation of type Q or E. Let me now precise what are not on this talk. So I'm mainly concerned about computing the Galois group in theory. So I mean that I will mainly say that this Galois group is so and so if and only if you are this kind of equation as a solution or not. So I'm not going to explain if or not it's possible to find such kind of equation. But in practice, to be able to compute the Galois group, you need to be able to solve two different problems. One which is a little more simple than the other. So the simple problem is to be able to find all the solution of in the ground field of a linear phi equation coefficient in K. And the second problem is to factorize the linear phi equation. So the second problem is much more complicated than the first one. So for instance, in the case of the shift case, you have very efficient algorithm to find a rational solution of a difference equation having coefficient in C of X. For the factorization of operator, you have to solve Riccati equation and things like that. And in the term of complexity, you fall from a polynomial to exponential case. So you have the complexity is less good, but it's possible in theory. So the case Q and S are quite similar, and case M and E it's much more complicated. So the factorization of Malheur operator is a work in progress with some of my co-authors. And for the elliptic case, it depends if you consider the equation in its Weierstrass form, and in that case, everything is very complicated. Or if you take a canonical version of the elliptic curve, and in that case, you can do something. So I was, at first sight, I was trying to say who was making all this result, but I realized that I have to cite a lot of people, and I will forgot a lot of them. So let's say that the second problem has been tackled by Petrovchek and Gosper, and a lot of people contributed in every aspect of the following hour. So let me precise what is the content of this talk more precisely. So as I said before, I assume that the characteristic of the field is 0. And let me define the field in K of elements that are invariant with respect to phi. And let us assume that it's algebraically closed. So it's the reason why in the example I've given, it was C of something. So you can replace C of something by Q of something. So if you want to make computation in practice, it would be quite beneficial. Let me also assume that K is a C1 field. So I don't want to recall what's a C1 field, but most field you are using to handle are C1 field. And last technical assumption is that there are no finite algebraic difference extension of K different than K itself. So it was the reason why in the Q case, I have to consider the ramification of the variable, because, for instance, in that case, you may take C of square of X, and then it will be an extension of degree 2 where you can extend your automorphism. So I want to avoid that. So it's the reason why I take all the ramification. And so this I pass away, but let me go back to it. So I will consider the order 3 equation. And I want to compute the Galois group. So let me precise what is the Galois group. But before I need to define what is a Picard-Vessiot extension. So let me translate the equation in terms of system. So the equation is implies the following system in a companion normal form. And conversely, you can, it's a cyclic vector lemma. Every system is equivalent to an equation. So an equation and a system is exactly the same, but so we have to make a choice, and we use the context of system. So let me denote by A the matrix of the system, and a Picard-Vessiot extension. So it's kind of the analogous of the splitting field in Galois theory. So it will be a ring. So it's not a field in this setting. It's a ring that contains all the solution of the difference equation. So there is U, an invertible matrix having coefficient in a ring R that solves the system. So in other words, you have a basis of solution of your system. So you don't have one solution, but you have three different solutions. And R is generated over K by U, by the entries of U and the inverse of the determinant. And the last assumption is that the only ideas of R stable under phi are just 0 and R. So we say that it's phi simple. And under those assumptions, Van der Poot and Singer prove that the Picard-Vessiot exists and is unique. So, okay, so to be precise, for showing the existence and uniqueness of the Picard-Vessiot extension, you only need the two first assumptions on this slide. So the two last assumptions will appear in a few slides. So now I've defined the Picard-Vessiot extension. I may define the Galois group. So it's the automorphism of R leaving K invariant, and that commutes with your automorphism phi. And very important result in the Galois theory is that you can embed your Galois group into a subgroup of GL3 of 3. So it's quite obvious if you map sigma to U minus 1 sigma U, it should be in GL3 of R, sorry. But in fact, the last assumption we make here implies that the element of R that are phi invariant belongs to C, the field of constants. And in fact, if you consider this matrix and if you make acting phi on it, you find that it's phi invariant. So this matrix has coefficient in GL3 of 3. So it's a presentation of the Galois group inside GL3 of C. But the non-trivial fact is that the image is an algebraic group. So it's defined by algebraic relation. And this algebraic group will measure the size of the Picard-Vessiot extension, the algebraic size. So bigger your Galois group is, and less algebraic relation you find among the solution. So as I said before, my goal is to compute the Galois group. By compute the Galois group, I mean compute its image as an algebraic group. Okay. So one of the potential application is to understand if solution of difference equation are algebraic or not. Okay, so from now, when I will say J, it will be the image of the Galois group as an algebraic group of J2. Okay, so now let me explain why I need two more assumptions on my ground field, meaning that K is a C1 field, and more important, you have no proper difference field extension. So it's a reduction theorem. So you may make a variable change, making that if I replace y by ty, I change phi of y is equal ay by a new system. So it's quite easy to compute the new system. So I just use the fact that phi is a morphism of ring. So I have a new system. And very important fact proved by Van der Poot and Singer is that you may change your system and you may force your system to be a point of the Galois group. So more precisely, it means that there exists an invertible matrix having coefficient K, such that after the variable change, your matrix is a K point of the Galois group. And the other point is that J over G0, so G0 is a connected component of the identity. So J over G0 is finite and cyclic. So for instance, it means that if you got a group, maybe it's a diagonal group, it means that you have a variable chain that will put your system into a diagonal system. If your Galois group is upper triangular, it means that you are able to find a Gauss transformation that will transform your system into an upper triangular system. So in fact, instead of computing the Galois group, I will explain how it's possible to find the matrix C and put your system into a K point of G. Because if you are a K point of G, it's much more easier to compute the Galois group. So the strategy in the order 2 case was already used by Hendrix in the shift case and the Q-difference case, and with Julien Roch we made it for the Malheur case, and no, so sorry, Roch did it for the Malheur case, and with Roch we did it for the elliptic case. So it's it's not the first time that this kind of idea is used, and let me stress the fact that you have similar strategy in the differential case. So in that case, it's not an algebraic point. It's you can put your system into some kind of Lie algebra of the Galois group, and this strategy has been quite useful to compute at least the connected component of the identity of the Galois group. So let me stress a last thing. So if you forgot the assumption, the last assumption, meaning that you have no proper finite difference extension of K, your matrix will have coefficient in the algebraic closure of K. So more or less you can do something, but I don't want to have trouble with algebraic extension. So the reason why I take from the beginning filled with no problem. So as a Hendrix situation, let me split the study into several cases, depending on the fact that the Galois group is reducible, primitive, or imprimitive. So I should precise something. When I say reducible, it should be reducible up to a conjugation. Because if you go back to this theorem, you mean that the representation depends on the fundamental solution you choose. If I choose another fundamental solution, I will find a Galois group that is conjugated to the first one, conjugated over C. So the Galois group is always defined up to a conjugation because you have to fix your fundamental matrix U. So let me assume that, that up to a conjugation, the Galois group is reducible. And by reducible, I mean that there is a proper invariant space invariant under J. So it means that J is composed by block upper triangular matrices. So since we are considering 3 by 3 matrices, this block may have size 0 or 2. Sorry, this block may have size 1 or 2. Okay. So there is a link between the fact that J is reducible and the factorization. So it was the reason why in the beginning I was assuming that we are able to factorize or not equation. So J is reducible if and only if the operator admits a non-trivial factor. And since your operator has order 3, if you have a non-trivial factorization, it means that you have a factor of order 1. And so it's a left or a right factor of order 1. But hopefully, we have a notion of dual. So I may transform L by its dual. So L is the operator, the order 3 operator. So I may define the dual as the following way. And you see that the dual is an anti-commutative morphism. So if you have factorization L1, L2, if you take the dual, it will give the dual of L2 times the dual of F1. So it means that if J is reducible, either L or its dual admits a right factor of order 1. So let me focus on the right factor for the one. So the equation has met right factor for the one if and only if you have a solution of so-called Riccati equation. So as you see, it's an algebraic difference equation. So at first sight, it's not very obvious to see how it's possible to solve it. But hopefully, in the shift case, Gottsper and Petkovšek show a very useful way to how to solve it. So let U be a non-zero element of K. So Petkovšek proves that it's possible to write U in a very specific way. So it will be the so lambda. It's so we are in the shift case. So lambda, it's a non-zero element in the complex in the constant case. So assume that it's complex, and B, C, and R are polynomial, and you assume that there are no common divisor between B and the iterate of C under the automorphism. So how you do that? You write U as a quotient of two prime polynomial, and then you apply shift to the denominator. And if you find a non-trivial GCD, then you multiply at the top at the bottom by R and phi of R to cancel this non-trivial GCD. And if you do that successively, you find this kind of writings. And if you plug U on that form on the preceding equation, so assume that U on that form. So the quite good thing is that since you have phi of R over R, here you will have phi of R over R, and then here you will have phi square of R over R because phi of R will be cancelled, and then phi to the 3R to R, and then you may multiply by R to find a linear equation. So it's exactly this formula. And if you use divisibility between B and phi of C, you find this condition. So B is the divisor of A0. Phi phi square of C is the divisor of A3. And R is solution of this difference equation. And it gives you an algorithm because you have finite number of divisors of A0, you have finite number of divisors of A3, and you have just to test every pairs of B and C. And for each pair of B and C, you just have to see to find a lambda and R. So if you have a solution, then you have a solution of your Riccati equation, and if every pair of BFC you don't have solutions, then you don't have solution of Riccati equation. So it's quite powerful, but on the other side, you have an exponential number of linear differential equation to treat. So the Q-difference case is quite similar, and in the Malloy case, it's a work in progress with Shizak, Duma, and Menzaroba. It's a little more tricky because you have 0 that is a fixed point, and the operator is blowing everything. So the degree is not the same, but it's possible to handle. And in the elliptic case, if you consider the equation written in various trash form, it's extremely complicated to check if there is a solution or not. But assume, at least in theory, that you are able to see if your operator factorize or not. So assume that you are able to find a U that is solution, and then you are able to write L as a product of another two equation and an equation of this form. So if you try to solve this equation. Then you will find that this equation is equivalent to this equation. So V and W are just the coefficient in L prime. So let me call A2 this matrix, and X this horizontal vector. And let me present general results that permits you to reduce a system which is a block triangular. So this general approach totally follow what we did in the differential case. So first of all, we reduce the block diagonal matrices. So I reduce the order 1 equation as this order 2 equation. So as I explained before, the order 2 case was already handled. So let's assume that it's possible to reduce this equation. By reduce, I mean finding the Gauss transformation that put this system into the Galois group, and the same for the other one. And then the tricky part is to reduce the block diagonal part. So I replace X by 0. So it can be done with Gauss lemma. So Gauss lemma basically gives you the algebraic group of G1 times G2, where G1 and G2 are algebraic groups. So you have a list of things to do depending on what is A2. So since you have a group of order 2s are quite few group that occur, so it's possible to do that. But if you consider equation of bigger order, it's not clear that it's possible to do that in general. But here we are order 3, so it's possible. And then once I've reduced this diagonal block, you have a theorem that states that you have a Gauss transformation that is unipotent. So with 1 on the diagonal. And let me precise how it's possible to find the Gauss transformation. So let me assume that the diagonal block system is in reduced form, and let me call GD this Galois group. So G is of this form. So it's block diagonal matrices. So C1 and C2 belongs to GD, and you have something on the upper right part. And now I will use this theorem, meaning that the Galois group is GD if and only if I have a Gauss transformation that transforms the system into a K point of GD, meaning that I can find T such that phi T A T minus 1 is a K point of GD. And in that situation, we can make the computation. So it means that so this matrix on the left is T. This phi of T. Sorry, it's T. So phi of T times the matrix times T minus 1 should be equal to a point of GD. So you have no choice. You have to put 0 and 0. And now I just have to solve this equation. So you know X. X was the vector 1, 0. You know X, you know A2, you know U, and you are looking to Y. You are looking to Y in K. And so if you are going to make the equation on the upper right part, you find that Y is solution on the following equation. So finding this T is just equivalent to solving phi equation in coefficient K. And so more group may occur, and in general, finding this T is totally equivalent to solve a linear equation in coefficient K. So it was the reason why in the beginning I said that you need some basic blocks. And the first one is to say that you are able to solve in the ground field equation having coefficient K. Okay, so let me, I don't want to details on the case of the reduction. So just trust me if I say you that in general, it's just solving in our equation. So in more generally, it's a little more complicated, but things work like that. So now let me assume that the group is irreducible, and let me consider the situation where the group is imprimitive. So a group is imprimitive if and only if you have a decomposition of C3, a proper decomposition of C3, such that J, the Galois group, is permitting your decomposition. So since you consider, so since elements of G are invertible, every VI have to be of the same dimension. And since we are considering order 3, which is prime, here every VI have to be of dimension 1. If you consider a primitive group of order not prime, things can be much more complicated. You have a lot of cases that may happen. So up to a conjugation, you find that J is a subgroup of the following. So Y is a subgroup of the following, because let me recall that J over its coordinate component is finite and cyclic. So it's a subgroup of permutations that contains an element, a non-trivial element, and that's fixed no one, and that is cyclic. So it has to be Z over 3Z, Z over 3. So it has to be of this form. Okay. So now to consider the imprimitivity, I need another criterion. So if I consider the system, I may iterate it. So I consider phi of y equals ay, and I may apply phi in the both sides of this equality 2 times. And then if I apply 1 time, so I will have phi to the 2y equals phi a times phi y, and I replace phi y by ay. So I find phi a y. And if I apply another time phi, I find this system. So let me call A3 this system. And it has been proved that if you iterate a system, the connected component is not moving. So this new system has exactly the same component as your original Galois group. So it means that if you are interested in the connected component, you just can iterate the system. And in fact, you can prove that if you iterate it sufficiently, you find something that is connected. So iterating is very powerful if you are just interested about computing the connected component. And if you assume that J is irreducible, you can prove that J is imprimitive if and only if the Galois group of this new system is diagonal. So how you can see it, sorry. So if it's imprimitive, then you have up to a Gaussian transformation, you can put your Galois group into something like that. And if you compute a matrix like that times 2 times itself, you will find something that is diagonal. Saying it otherly, in other way, every element of G makes a free cycle on the VJ. So it means that if you iterate 3 times, you find on the identity. So it means that you are block diagonal. So we have a criterion to check if J is imprimitive or not. You just consider the equation that is generated by that, and you just have to say if it's irreducible or not. Since we are considering group of prime order, so I have 40 minutes, right? So I will finish in a few minutes. So since you have a group of prime order, you don't have a lot of choice. So I recall that so J is imprimitive And J over the 0 is finite and cyclic, and the order is a prime number. So we have generalized the result of Hendrix for prime number. So Hendrix proves this result for order 2 case, but you can do it in general. And in fact, you have a dichotomy. So if the determinant of J, so is the image of J under the determinant, so you can prove that it's an algebraic group of GL1 of C. So it's finite or it's C star. If it's C star, then it's very simple. So you have everyone in the Galois group. So you have a thing like that. So A1, A2, and A3. And you also have D squares. So D squares will be there, and there. And D to the 3. So you have all possible elements. The second situation is that when the determinant is Z over NZ, and N is co-prime with 3. So in that case, you have this assumption that the product of these 3 elements is a primitive n square root of unity. And the last case, when it's not co-prime, then it's 3n primitive root of unity. And so you can prove that the determinant of J is just the Galois group of this order 1 equation. So it's possible to compute the Galois group quite easily. In that case, you just have to compute another 1 equation. Okay, but it doesn't explain you how you find your goal transformation T. So as I said before, if you are imprimitive, then the order 3 equation is reducible. So it means that you have a Riccati equation corresponding to the 3-2 equation. So let me call D any solution of this Riccati equation. And then you can prove that your equation is equivalent to this equation. And if you look at it carefully, this equation is just equivalent to phi to the 3 of y equals dy. So it can look complicated, but in fact, it's a phi-free equation of order 1. And so let me now reduce the order 1 equation. And now you can prove that your reduction matrix is of the following form. So with a Gauss transformation with a diagonal F11. And if you consider the product of this kind of element, you find that if it has to be a root of unity, then the product will be a root of unity. So, okay, so it's possible to reduce the system for in the imprimitive case. So let me very quickly finish with the primitive case. So again, the situation is much more simple since we are looking on equation of small order. So at this stage, for order 2 cases, the situation is very simple because you find that J equals to the determinant of J equals SL2. So you just have to compute the determinant of J. But for order 3 case, the first problem occurs because you have 2 groups. You have SL3 and you have SO3, which is a special orthogonal group. And when you will consider equation of bigger order, you will have a lot of primitive groups that may occur. So we need a criterion that tells you if you are in the SL3 case or in the SO3 case. And let me sketch just how we do if the Galois group is SO3. So the Galois group is SO3 if and only if you can find a Gauss transformation that puts your system into an element of SO3 over K. And the element of SO3 over K satisfies a very convenient equation, meaning that B times the transpose of B is the identity. So I never know if in the English system I should put the transpose on the right or on the left. So here it's on the right, and I'm deeply sorry if it should be on the left. And if I consider the inverse of T, you find that you have this matrix. So you have to find the system. So the system is quadratic in the entries of P. But in fact, if you see it more carefully, you can find that P times transpose of P is a symmetric matrices. And in fact, we can prove that it's sufficient to solve AX transpose of A equals phi of X, where A is a symmetric matrix. So, and again, it's just solving a linear equation. And if J is not SO3, but something bigger, you have similar computation. So, if you want to compute the Galois group in practice, you have a lot of short paths. So, for instance, if you consider it in the Q-difference case or in the shift case, most of the times you are able to compute the local Galois group. So you have a lot of density theorem in different Galois theories that say that this kind of element is an element of the Galois group, and the IC closure is a Galois group. And why I say that? Because if the Galois group is SO3, it implies that the eigenvalues of the matrix of the Galois group are quite special. So if you are able to solve, to compute the local Galois group, which is in practice much more easier, then most of the case you are able to withdraw that case. So this solves the problem for the free case. So in general, so our next aim is to, after we have finished this work, is to be able to produce at least a theoretical algorithm to compute the Galois group. So Feng did that, making an analogous of Rorschach's algorithm for different cases, but this algorithm is not practicable in practice. So this algorithm that is improved by Sun and other people in this seminar. So if we want to be able to solve this this problem in practice, we should work more and probably better understand what are the classification of primitive group. But my time is over, so I should thank thank you for the invitation, and I will answer to your question if you have some.
Thank you very much. I'd like to thank the speaker. So yeah, please, if anyone has questions, unmute yourself and ask, or type into the chat. I see Michael.
Yes, I have a question, and it was on slide number 16. You can go back to that.
Yeah.
So I'm a little confused. Are you claiming that in the reducible case, you can always reduce to a block diagonal matrix?
No, I say that to be my strategy is first to reduce the block diagonal matrix, and then reduce the entire system.
I see. So
if you don't reduce the block diagonal matrices, your ground transformation will have something on the diagonal. So in some sense, you do that on two steps. So first you find the diagonal block, and then the upper right block.
I see. Okay, now I understand. Thanks very much.
You're welcome.
So you want to split A2 further, correct?
Yeah.
That's what you do.
Yeah, and the problem is that if you consider a bigger system, you will have a lot of groups that may occur, and it will be in general very difficult.
Why did you stop at order 3?
So there are many reasons. So the first one is that I use the order 3 to better understand what will be the techniques to be able to solve the general situation. Because as I explained at the end, when you start with order 3 case, it's the first time where very nasty problem occur. And to be honest, if I have to look up neural strategy, I think I will not try to compute more than the identity component, because, for instance, this theorem, when you consider equations that are not of prime order, it should be awful, because you don't have necessarily a block of size 1. You can have block, for instance, 2 blocks of size 2, and so you have a lot of choice to separate. So I think that in general situation, at first sight, I will try at least to compute the identity component. But in general, it's very complicated, I think.
Thank you. And how about computing the Lie algebra?
So the Lie algebra appear naturally in the differential case, because if you consider a differential system, then in some sense the system belongs to some kind of Lie algebra, and you have a transformation that minimize the size of this algebra, Lie algebra, and at the end you fall into an algebra that is the algebra of the Galois group. If I'm not mistaken, this theorem does not exist in the difference case. So the real analogous is this Van der Put-Singer theorem.
Thank you.
Any other questions? Just unmute yourself or type into the chat. Okay, if there will be further questions, we can discuss them after the breakout room.